Hello again! In this video, we will dive into the challenges and possibilities of extending the lifetime of wind turbine blades, focusing on their life cycle management. Specifically, we will look at the R-ladder, an approach that focuses on reducing waste and promoting a circular economy for materials. We'll explore how composite materials in wind turbine blades pose unique challenges for repurposing and recycling, and the solutions being developed to overcome these issues. The key themes in this video are lifetime extension, reuse, remanufacturing, repurposing, and recycling. These are part of the R-ladder, which is a framework that categorizes different stages in the life cycle of materials, from reducing material use, rethinking, to reuse and recycling. When looking at options for materials, it is advisable to prioritize the higher levels of the R-ladder, which appear darker on the slide. In the context of wind turbine blades, these stages become crucial as we aim to extend the useful life of blades and minimize the environmental impact associated with their disposal. Wind turbine blades are primarily made of composite materials, often consisting of glass fiber or carbon fiber with a resin matrix. These materials are lightweight, durable, and resistant to weathering, making them ideal for wind turbine blades. However, their durability also poses a challenge when it comes to end-of-life management. In the next slides, we're going to take a look at how each stage of the simplified R-ladder can be applied to wind turbine blades. Let's start at the highest and most desirable level, lifetime extension. Wind turbine blades are designed to last for around 20 to 30 years, but there are opportunities to extend this through proper maintenance, inspection, and repair. By investing in proper maintenance, small repairs can be made to prevent larger, more costly damage. For instance, coatings are reapplied to improve durability, and routine inspections can identify early signs of damage or wear, allowing for preventive maintenance. In some cases, parts of the blades can be repaired, such as patching cracks or reinforcing sections that may have weakened over time. And what if we could design the future blades in a modular section rather than one large structure? Then we could use the full potential of repair and maintenance by taking out sections that have damage and replacing it by new ones. Once the turbines reach the end of their economic life, they are often dismantled. This brings us to the next stage in the R-ladder, reuse. Reuse refers to reusing blades as blades, for instance on another turbine, or reinstalling the entire turbine somewhere else. This approach could apply to wind farms where turbines are decommissioned after many years of operation. In this case, it would be important to know the remaining useful life of the blades, and could involve refurbishing blades by making modification to extend their operational life. We now move to the next R on the R-ladder, which is remanufacturing. That means that we use parts of a discarded blade into a new blade. We do that by disassembling the old blade and reusing parts into a new blade. For remanufacturing for blades to work, we need to work with materials or parts that can easily be separated from each other, while still keeping their functionality. Let's take a look at what that means for the composite materials in our blades. The choice of composite materials and their strength lies in a combination of fibers and matrix, and the adhesion between these two materials. This makes them difficult to separate and reprocess into new products. This is a significant barrier to remanufacturing, as the mixture of different materials creates a closed-loop situation where they cannot easily be recycled. For example, the long fibers in the wind turbine blades give them their mechanical properties. These fibers are crucial for maintaining the blade's strength and stiffness. The thermoset matrix undergoes a non-reversible chemical reaction during manufacturing and makes the blade maintain its shape during its lifetime. The resulting composite material becomes very difficult to separate and reuse without sacrificing its mechanical integrity. The fibers, and especially their length and orientation, must be preserved for the material to retain its performance, which creates a trade-off between the mechanical properties and recyclability. One innovative approach being explored for the remanufacturing stage is the use of thermoplastic matrices, which have reversible properties by applying heat and pressure. They can be reshaped, remolten, and reprocessed after the blade has reached the end of its life. This allows for the reuse of the materials without compromising the strength of the original components. To address the challenges of composite materials in wind turbines, we need to rethink how blades are made from the outset. This involves selecting alternative materials that allow for modularity in the blade design, that can easily be repaired, can be remanufactured after their lifetime in the blades into new materials for blades or other products, are more recyclable, or that can be separated more easily at the end of life. What we can't forget is that the blades that are decommissioned now are probably 3 to 4 times shorter than the ones that are used today. So for remanufacturing to work, we would definitely need a material that can change shape after its lifetime in the blade. Thermoplastic matrices, for instance, could allow blades to be more easily disassembled and the materials separated for reuse and recycling. Let's take a look at the fourth stage, repurposing blades. This refers to finding new applications once they are no longer suitable for their original function as a blade. For instance, wind turbine blades are being repurposed for various infrastructure projects, including bridges, sound barriers, playgrounds, or public art installations. Their strength and size makes them excellent candidates for these type of projects. Finally, we arrive at recycling. Recycling is the last step in the R ladder and is another challenging stage for wind turbine blades. The composite materials in blades are extremely durable, and this durability also makes them difficult to recycle. Different research strategies are being followed to tackle this. In some cases, shredding blades into smaller pieces has been used to create secondary raw material sources. This process can result in a loss of the original material properties due to the reduction in the length of the fibers. The recycled material, therefore, is not very suitable for high-performance applications. Another area of interest is the use of natural fibers, such as flax, bamboo, hemp fibers, as reinforcement for the blades. They capture CO2 during their growth and are more biodegradable at the end of their life. This comes at a price of the lower mechanical properties of these fibers. When we really want to start separating the fibers from the matrix they're embedded in, there is promising research into methods like pyrolysis or solvolysis. Pyrolysis uses heat and pressure to break down materials and separate matrix from fibers, enabling more efficient recycling. Solvolysis uses chemicals to break down the matrix around the fibers. Both processes result in chemical building blocks for new matrices and lower fiber properties. Though these processes are not yet widely implemented, it could hold some potential for improving the circularity of wind turbine blades. As we have seen, extending the lifetime of wind turbine blades, reusing, remanufacturing, repurposing, or recycling them all involve significant technical challenges. But there is also considerable potential for innovation. By improving life cycle management, rethinking blade design and the material choices, and advancing recycling technologies, we can help make wind turbines more sustainable and circular. The research and development in this area is ongoing, and there's much to look forward to as new materials and new ideas are taking the spotlight.